Today we are going to start a new unit on magnetism. This is going to be a fairly short unit compared to our other units, so a couple of weeks we'll be ready for another unit test. Before we talk about magnetism, however, we have to kind of take a look at where magnetism comes from. I wanted to define a new term for you called a magnetic domain. A magnetic domain is a tiny little region inside what we call a ferromagnetic material that is represented by arrows. Now, you read that definition, and that's not going to make much sense to you, right? You can recite that for me if you're good at remembering things, but it's not going to mean anything to you. Let me help you make meaning of it here. Okay? Let's identify what a ferromagnetic material is. Just stop writing for a second. I'll give you a chance to write it in a second. A ferromagnetic material is a material that can become magnetized. So some materials can become magnetized, some can't. The leg of your desk is made out of steel. Steel is a ferromagnetic material because steel is an alloy of, do you know what steel is made out of? What's the prime ingredient in steel? Iron, right. What's the chemical symbol for iron? Fe, ferromagnetic material. Okay, steel is a ferromagnetic material because it's made out of probably the most commonly known ferromagnetic material, iron. Right? So it can become magnetized. When you put a magnet up to it, the magnet's going to stick to it because the leg of your desk can become magnetized. Same with our whiteboard up here. Same with the frame around the doorway over there. But if you put a magnet nearby the back wall, or if you put the magnet on the floor, it's not going to be, or a piece of paper, it's not going to be attracted to it because those things, the wall, the floor, aren't ferromagnetic materials. A ferromagnetic material is a material that can become magnetized.
Like most normal metals on a grid scale.
Well, you could be careful about that. Like we talk about. Sometimes we get magnetism and electricity mixed up, and we think, oh, something's a good conductor, like it's a metal, then it's going to be ferromagnetic as well. It can become magnetized. No, not at all. Copper is a great conductor, but it's not ferromagnetic. Okay, it can't become magnetized. So I wouldn't say at all that most metals can become magnetized. Honestly, I can't remember the list, so I can't remember which ones can and which ones can't. But I wouldn't say all of them could be at all, or even most of them could be at all. There's lots of metals that aren't ferromagnetic. Like there's lots of metals that are ferromagnetic as well, but certainly lots that aren't. Probably the most common, again, would be iron, and this is the way you can remember this one, right? Because iron is chemical symbol Fe, which comes from the Latin ferrous, okay, which is also the base of the word ferromagnetic. So you remember iron is ferromagnetic. Steel is an alloy of iron, so it's going to be ferromagnetic as well. Now, you're not going to have to remember an exhaustive list of what's ferromagnetic and what's not. Okay, if you're given a question on a test where it matters, you'll be told that this material is ferromagnetic or isn't ferromagnetic or whatever the case may be. So now we've got a magnetic domain is defined as a tiny little region inside a piece of steel, not inside a piece of paper, inside a piece of iron, not inside a piece of concrete. A tiny little region inside a ferromagnetic material that is represented by arrows. Now, we're not suggesting that if you look at a piece of steel under a microscope that you're going to see all these tiny little arrows pointing in different directions, but rather, if you could look at it detailed enough, which we actually can't with a microscope, but if we could, then we would see similar patterns of spins of electrons. In those similar patterns of spins, we represent in a way that we can visualize with arrows. Okay, so these similar patterns of spins are domains, but because we can't actually physically see those with our eyes under a microscope, we're simply going to represent them with an arrow. Okay, if we get a certain pattern, we represent it as an arrow pointing this way. Another pattern, we represent it as an arrow pointing another way. So here's our ferromagnetic material, a piece of steel or a piece of iron or whatever. Here's our tiny little regions, although they don't look so tiny on this, but pretend they are. Each of these domains has these electrons inside it. The details of that you don't need to know. That's beyond physics 30. Okay? You just need to know that these tiny little regions, these domains, are represented by arrows. And these arrows can be pointing in all kinds of crazy, different, random directions. This is a ferromagnetic material, but this is a non-magnetized ferromagnetic material because the domains are pointing in, well, more or less random directions. It still has the potential to become magnetized, but it isn't magnetized right now. It just has the potential to become magnetized. Now I've got that ferromagnetic material that for some reason is going to become magnetized. Now, when it becomes magnetized, these domains start pointing not necessarily completely in the same direction, but in similar directions. So what we're going to do is start erasing these puppies here, these domains, these areas of the electron spins that are represented by arrows, and start drawing them in more or less similar directions. This is a magnet. They're both ferromagnetic materials, but one is magnetized and one is not magnetized. The bottom one is a magnet. Now, how did it become a magnet? How did you get these domains pointing in the same direction? Well, there's a couple ways. What's one way where you can turn something from a non-magnet but ferromagnetic material into something that is a magnet? You might know the answer to this. You probably do, actually. Blake? No, but you're close. Blake said, could you run a current through it? Using an electric current can generate a magnetic field. In fact, it will generate a magnetic field, but it's not a magnetic field in the conductor. It's a magnetic field around the conductor. So we wouldn't want to run a current through this ferromagnetic material, but what we could do is wrap wire around it and run a current through that wire that was wrapped around it. Then the magnetic field that was generated by the wire could cause these domains to point in a similar direction and magnetize it. If I wrap the wire around like loops like this, if I just randomize the wire, then the magnetic fields would probably end up canceling out and would be left with more or less the same thing. Does that make sense, Blake? We'll talk a little bit more about the relationship between electricity and magnetism in a couple of days. Okay? For now, yeah, Blake, you could wrap some wire around it, apply an electric current through that wire, and you could cause it to become magnetized. But what's the simpler way, the easier way? The way that you guys have done before, whether you realize it or not. You've done it before. In fact, you've probably done it this week at some point, maybe even today at some point. You put a fridge magnet on the fridge. You put a magnet, any kind of magnet on something that's not magnetized. Well, that's something that's not magnetized. Test the filing cabinet there, yeah. He just did it. Dryden just did it. Just now, he just did it. He put a magnet on the leg of the desk. That magnet has domains that are already aligned. When he puts it near or on the leg of the desk, what it does is, well, in that case, it temporarily aligns the domains. Okay, let's say that this is Dryden's magnet that he's bringing nearby or touching the leg of the desk with. What does that do? What causes these domains that were pointing in random directions to start aligning with these domains that were in the magnet. So it becomes temporarily aligned, right? We just made a magnet. Okay, the leg of Dryden's desk has just become a magnet. Magnets will attract non-magnetized ferromagnetic materials because we temporarily align domains in them and make them temporary magnets. Now he's taken that magnet off, so the leg of that desk has probably gone back to a non-magnetic state, and the domains are pointing in random directions. But while it was there, so now it's probably gone back to this, right? But while it was there, he caused the domains in that local region of the leg of the desk to align themselves with the magnet that he put on it. It became a magnet. Magnets attract magnets, right? Well, yeah, magnets sometimes attract magnets. Magnets sometimes attract magnets. Magnets sometimes repel magnets. But just like charged objects will always attract neutral objects, magnets will always attract non-magnetized ferromagnetic. They're never going to repel. Magnets, like Dryden put on a leg of his desk, will always attract non-magnetized ferromagnetic materials because that magnet will temporarily align the domains in that non-magnet. Does that make sense? Just like, remember, the charged object will temporarily cause a separation of charge in the neutral object, causing attraction. So we can have repulsion, but not in that situation. Okay, when you bring a magnet nearby a non-magnetized ferromagnetic material, it's always going to attract. Now, let's take a look at polarity here. We talked about negative charge and positive charge in our last unit. In this unit, we're not. This unit, we're going to talk about poles, north poles and south poles. Okay, it's getting close to another couple months. It's Christmas time, so let's start talking about north poles and south poles here. This doesn't have any polarity associated with it because the domains are essentially random. It's non-magnetized. This one does, as does this one, at least right now, while the other magnet is nearby. We define the domains as pointing from south to north. So we arbitrarily call this left side the south pole. I mean, we could have called it the north pole, but by convention, it's defined as the south pole. We could have called it the Q pole, but by convention, it's defined as the south pole. It's just a name, though. Similarly, for this one, we'd call this the south pole, and we call this the north pole. Unlike electric charges, you can't have just one. Like, it's no problem to have one positive, right? Or to have one negative charge, an electron. You can't have just a south. It always goes with a north. Imagine what happens if I take this and I cut it in half and it becomes two magnets. It's not a south magnet and a north magnet. And because the domains point from south to north, it would become a south and north magnet and a south and north magnet. You're always going to have two poles. You can't have what we call a magnetic monopole, single pole. You have to have two poles. Okay, make sense? Yeah, all right. Let's give you the laws of magnetism. We already went through one of those, and the other two should be pretty familiar to you from your electricity unit. First law, we say that like poles of a magnet repel. What do we mean by like poles? Give me an example of two like poles. South and south repel each other, push each other apart. North and north repel each other, push each other apart. Don't say positive and positive. That's a different thing. They push each other apart as well, but that's an electrical interaction, not a magnetic interaction. There is a relationship between electricity and magnetism, because remember what those domains are caused by, spins of electrons. Okay, but not on a macroscopic scale so much. Like poles will repel each other. Unlike poles of a magnet, i.e. north and south, south and north, will attract each other. They'll pull each other together. Now, that's not what's happening when Dryden puts his fridge magnet up against the leg of his desk, right? It's attracting, but it's not opposite poles attracting. It's a magnet attracting a non-magnetized ferromagnetic material in the leg of the desk. That's the third law. Magnets, well, we say both north and south poles of the magnet. In other words, magnets will attract non-magnetized ferromagnetic materials. Dryden's magnet will attract the leg of the desk. And it happens because when he brought that magnet nearby the leg of the desk, it caused the domains in the leg of the desk to become aligned with the magnet that he already had, the fridge magnet, the permanent magnet that he already had. It temporarily aligns the domains in the non-magnetized ferromagnetic material. It's important to mention this, the non-magnetized ferromagnetic material. Because if Dryden brought that fridge magnet near a piece of paper, what would happen? Nothing. You can't align the domains in a piece of paper because there aren't any there. Now let's talk a little bit about magnetic fields, somewhat like electric fields. In fact, there's a lot of similarities between electric fields and magnetic fields, just like there is between gravitational fields and electric fields. A lot of similarities. But they're not the same thing. a magnetic field, just like you guys remember 2 days ago on your unit test for electricity, question number 1 asked you to define an electric field. Do you remember what that definition was? Yeah, it was a region in which a charged object could experience an electric force. Well, a magnetic field, we're going to define as a region in which a magnetic force could be experienced by a magnet or by a ferromagnetic material. So it's almost the same, right? Except our experiencer would be a magnet or a ferromagnetic material as opposed to a charge. A region in which a magnetic force could be experienced. Could be, right? Could be. There's a magnetic field in front of you right now caused by the Earth. There's nothing there to experience it. But if there was something there to experience it, it would experience a magnetic force. So it's a region in which a magnetic force could be experienced if there was something there to experience it. Now, where do we get magnetic fields? Well, we get magnetic fields surrounding magnets, which the Earth is a magnet. It's a pretty weak magnet. It's a very weak magnet, actually, in the grand scheme of things. But it's still a magnet. What causes the Earth's magnetic field? We're not actually completely sure still. Like, we know that it's weakening and the field is weakening, and then sometimes it reverses over hundreds of thousands of years, but we're not actually 100% positive what causes it. We know that it has something to do with churning magma, ferromagnetic material, liquid down within the Earth. We're not 100% sure exactly the mechanism by which the Earth's magnetic field sustains itself. But it does, more or less. And it's also caused by moving charges. Blake said a little while ago, he said that we could magnetize a non-magnetized ferromagnetic material by applying a current through it. And he was almost right. He said we could wrap a wire around it, and we said that was because when we apply a current through the wire, it generates a magnetic field. Well, that's because moving charges, the moving electrons within the wire, generate the magnetic field. We'll talk more about that a little bit later, okay? You don't need to know the details of that, just that it happens right now. What I'm going to do with you right now is try to illustrate the shape of magnetic fields surrounding magnets. So what I'm going to do is give each of you a piece of paper, a template, which has a magnet on it, and it also has a pair of magnets, north against south, notice. And notice it has another pair of magnets, north against north. And I want you to sketch the magnetic field that surrounds these different scenarios. The way that you're going to do that is to place a magnet in groups of 2 or 3, well, with the number we have, probably groups of 3 or 4. Place a magnet in the middle of your desk. The reason I want you to put it in the middle of your desk, as opposed to at the edges of your desk, anybody want to take a stab at that? Yeah, there's ferromagnetic material underneath the edges of your desk. So put it as far away from the edges as you can. Put it in the middle of your desk, okay? Put the magnet in the middle of your desk and orient it like it is on the template that I'm going to hand out to you in just a second, like you see up on the board here right now. And everywhere where you see a star, I want you to place a compass. And you're going to draw with a little short arrow which way the compass needle points. So you put a compass right here, the compass needle points this way, draw a short little arrow indicating that it's that way. You put it right here and it points this way, draw a short little arrow. Don't draw a long one, draw a short little arrow indicating that it points that way. And then, once everybody's done that, we'll come back together as a group and do a little kindergarten work here and join some dots and see what kind of pattern, see if we get a nice little picture of a dinosaur or something out of it, okay? I hope we do get a picture out of it that we can recognize as a pattern. Probably won't look like a dinosaur, I got to be honest with you. All right? have some sound. After we've completed our activity, we should have gotten our arrows pointing more or less like this. We'll do a little kindergarten work now, join some points together, and see what kind of picture we get out of this, see what kind of image we get out of this. Okay, so I'm going to start drawing my lines like this. You can see that these arrows are pointing like this. They're always pointing away from the north. They're always pointing towards the south pole of the magnet. This is going to look a lot like diagrams you do in our last unit for electric charges. You don't need to draw this diagram that I'm about to draw here. I just want to draw a comparison between what you've just seen and what we did in the last unit. If I pretend I've got a positive charge right here and a negative charge right here, and I start drawing the field between them, it's going to look like this. The electric field goes from positive to negative, away from the positive, toward the negative. Doesn't that look an awful lot like the magnetic field surrounding a bar magnet with a north and a south as opposed to a positive and a negative? Now the one difference that you notice with this is that although outside of the magnet the magnetic field goes from north to south, inside the magnet it continues in that loop, right? Continues in a loop going around like this, and ends up going from south to north. And if you remember when we drew our magnetic domains, we said the domains pointed from south to north. So inside the magnet, the domains or the magnetic field, Nathan, the domains or the magnetic field are pointing from south to north, but then outside of the magnetic field points from north to south. And again, you can see that the shape of that is remarkably like the shape of the electric field surrounding a positive charge and a negative charge. Now, what do we get? What do we get in this next one? We got arrows all over the place in this one. We got a north pole and a south pole. What would you expect to happen here first, before we draw our little fields, our little micro fields here? What would you expect these two magnets to do? They should attract each other, right? Because north attracts south. Let's draw some little arrows here. Going to look something like this. Okay, it's not going to be perfect again, but going to look more or less like this. Start joining some dots together here. Not going to get a picture of a dinosaur like we did in kindergarten, but we should get something that's recognizable. Field lines are going to go around like this. Again, from north towards south, always away from the north, always toward the south. That is, when we're dealing with outside the magnet. Inside the magnet, we couldn't really draw that with the experiment that we just did, but inside the magnet, it would point from south to north. Outside, north to south, inside, south to north. The magnetic domains go from south to north, so that's which way the field would go, inside. Now, this would look remarkably like electric field diagrams if we had a positive, a negative, a positive, and a negative. Remember what we said about electric fields? Sometimes you don't remember what the shape of the diagram should be like. Remember we said, though, that if two charges attract each other, the electric field lines should fill in the blank. Should what? Join together. Well, these two magnets attract each other, right? North and south. Look what happens to the field lines in the middle there. They join up, just like a positive and a negative join up for electric fields. Okay, let's draw our last one here. This time we got north against north. Our field lines should have looked something like this. And again, yours might not be exactly like this because your compass wasn't a point source. It's easy in theory to say what it should look like. Let's join some dots together here. What do we see here? I'll draw a couple more in here. What do we see in here? Well, the field lines A are going from north to south, as they should outside of a magnet. Of course, inside the magnet, they should go from south to north, but we're not drawing those. What do you notice about these field lines in the middle here? In between the north and the north. They're going away from the north, right? Where are they not going? What are they not doing? They're not merging together. They're not joining up together, which means that we're going to get a force of repulsion. And we should get a force of repulsion here, right? Because it's north and north. Remember that. For electric field lines, for magnetic field lines, if the field lines merge or join up, then we're going to get a force of attraction. If they don't merge or don't join up, then we're going to get a force of repulsion. You could get a question on a test that has some kind of crazy scenario of magnets set up. One that we sure didn't do in this little activity that we just did. How do you know if the question says, do they attract or repel? How do you know? Well, easy. If the field lines join up, then they attract. If the field lines don't join up, then the two magnets repel each other. All right, we're going to define the direction of the magnetic field here, and then we're almost done for the day here. There is a direction associated with the influence of the magnetic field, so it is a vector field, just like a gravitational field, just like an electric field. Now, we're going to define the direction of the magnetic field in two ways. The first way, this is what you just did in your little activity. We saw which way a compass needle would point. The direction which a compass needle, let's say the north end of a compass, because that's the compass needle. The red tip of the compass, if a compass is functioning properly, is the north end of the compass. So the magnetic field is the direction which the north end of a compass or the compass needle would point when placed in the magnetic field. That's how you guys label the diagrams in the activity. But we saw in the diagrams that we drew from that activity that the magnetic field always also goes, when you're outside of the magnet, that is, away from the north and toward the south, just like it went away from positive and toward the negative in the context of an electric field. Now, inside the magnet, it would actually go from south to north, but we rarely talk about inside the magnet. All right, let's take a look at the next page. You don't have to copy this next page down, okay? Next page just shows us different strengths of magnetic fields. We don't have to memorize these numbers, but it is helpful to have kind of just a general concept of strengths, right? I know that if I'm moving 100 kilometers per hour, that's pretty fast for a car. I know that if I'm moving 2 kilometers per hour, that's pretty slow for a car, right? We have a concept of values of speeds. We don't really have so much a concept of values of magnetic field strength. By the way, magnetic field strength given by the symbol B, measured in the units T, Tesla. The magnetic field strength surrounding the Earth, it varies depending upon where you are on Earth, and it's changing constantly, but on average it's about 10 to the minus 5 Tesla. So it's a pretty weak magnetic field. A bar magnet, typically, after you remagnetize it here, probably 10 to the minus 2. So it was about 1,000 times stronger than the strength of the Earth's magnetic field. That's why when you put your compass, look, if I hold my compass right here, which way does it point? Like the Earth's magnetic field, right? But if I bring that bar magnet nearby it, the Earth's magnetic field barely affects that compass, right? The bar magnet affects it way more because the bar magnet has a strength that's about 1,000 times stronger than the Earth's magnetic field. Way stronger. Typically, at least. Way stronger. 10 to the minus 2 Tesla. Sunspots, like this magnetic activity that takes place on the sun, 10 to the minus 1 Tesla, 10 times stronger than a bar magnet. An MRI. Who's ever had an MRI? When you have an MRI, they have you fill out this form, right? This big, long, detailed form. Crazy questions like, have you ever had shards of metal stuck in your eye? Like these obscure things, right? I don't know what they'd do if you did have shards of metal stuck in your eye. They ask those questions because If you happen to have, imagine put your head inside one of those things with a magnetic field strength of 15 or 10 to the positive 1 Tesla. Like that's crazy strong, right? That's 1,000 times stronger than the bar magnet. And you've got ferromagnetic metal shards still stuck in your eye. That could be a problem. Hey, if you answer yes, I'm not sure what they do. Okay, but they've got to have some way of administering that. The strongest human magnet ever made, that's also 10 to the 1. Hey, it's twice as strong as an MRI, but it's still same order of magnitude. Now, this is what you do not want to get close to. Okay, this is what you do not want to get close to. A magnetic neutron star is 10 to the 11 Tesla. Like that's probably, I would think, strong enough to literally suck the iron out of your blood and cause you to suffocate or cause you to die because the oxygen doesn't go to your brain. The good news is, if you're on your way to a magnetic neutron star, you would die long before the iron ever got sucked out of your blood. So you wouldn't have to deal with that. Okay, you'd deal with death in another way, probably. It's crazy high, right? Clearly, if we solve for a magnetic field strength, and we get a magnetic field strength that is somewhere like north of 10 to the 1, like we're probably wrong, right? We've probably made a mistake somewhere. So you don't have to memorize these numbers, but know that if you get a really big number like this, in most cases, it's wrong, especially if you're talking about a magnetic field around the Earth or something like that. Does that make sense? Okay, last thing. This is going to rock your world. This is going to close the door. Okay, going to get you to close the door because I don't want this secret to get out here, okay? This is going to flip everything that you've ever trusted. Okay, everything that you've ever trusted. If we define if we define the magnetic field as being the direction that a compass points, then the compass would point this way, right? Compass points towards the North Pole. But if we define it as being from north to south, away from the north toward the south, what does that mean? Well, it means that this area up here in Canada isn't really magnetic North Pole. Geographically, it's north, but magnetically, it's actually south. And magnetically down here is actually north. So what we're really saying here is that, like, even though, navigationally, people say that's north, okay? It's not really north. It's really magnetic south. It doesn't really matter as long as we're all using the same frame of reference. As long as we're all calling it the same thing, it doesn't really matter that we're all calling it the wrong thing. But technically, that's magnetic south. Geographic north, magnetic south. But, listen, the end result of this is that, like when you're 6 years old and you write your letter to Santa Claus, okay, and you're not getting what you want, okay, it's because maybe, just maybe, where'd you send it? You sent it to the North Pole. Where does Santa Claus live? He lives in the South Pole, right? You sent your letter to the wrong place. Okay? Magnetic North Pole. You got a bunch of penguins down there right now laughing their heads off because they got all these letters to Santa and they know all these little kids around the world aren't getting their gifts because you sent the letters to the North Pole. And the penguins live in the North Pole, laughing at the big joke. Santa Claus is up there wondering, where are all the letters? Nobody's sending me anything. Because Santa Claus lives in the South Pole. Magnetic South Pole. Geographic north, magnetic South Pole.